Self-induction. Okay, let us consider these two figures, figure A and figure B. So first we will look at this figure A. So in this figure A, we have a coil and it is connected in series with a cell through a tapping key. Okay, so when the key is closed, the current I starts flowing through the coil. And this current, it is actually like this. You know, when the key is open, then the current is 0. But when you on the key, the current starts increasing, right? From 0 till it become maximum. But the time taken for the current, to increase its value from 0 to maximum, right? It is a very small time, maybe in terms of microsecond. Though the time is small, but it's very important in this case. Because during that period, when the current is increasing, so as the current is increasing, what will happen? The magnetic flux inside the coil will change. Okay, so because of the changing magnetic flux, what will happen? The current will be induced in the coil. And this induced current in the coil, it will be opposite to the directions of the current which is sent by the cell. So I have indicated here that this I is the current produced by the cell and the induced current will flow opposite to this. Okay, so similarly in figure B, if you open this tapping key, what will happen? The current starts, decreasing from maximum to 0. It starts decreasing. So during that decreasing time, again in this case, you will find that there is a change of magnetic flux. That means the magnetic flux here in this case is decreasing. So that decreasing magnetic flux will again produce what? Will set up a current in the coil, or we can say a current is induced in the coil. But the directions of current in this case, it should be along the same as the directions of the battery current. Okay, so if this is the current which is sending by the cell, then when the current, right, is decreasing, when the cell is open, when the circuit is open, then this induced current will also flow in the same directions as the directions of the battery current. Okay, so here we can say that an EMF is induced in the coil. So this EMF which is induced in the coil, it is known as self-induced EMF, or we can say back EMF. Self-induced EMF, or sometimes we call back EMF. Okay. Now, and this phenomenon of production of induced EMF due to a changing current in the coil, that phenomenon is known as self-induction. Okay, all right. At any instance of time, this magnetic flux which is linking with the coil, it is found to be directly proportional to the amount of current that is passing through the coil. Or we can say phi is equals to some constant, and the constant here is L times I. What is L? L is a constant of proportionality and it has got a name, and we call it as coefficient of self-induction, or we can simply call it as self-inductant. So what is L? L is self-inductant. Okay, all right. So if this is the magnetic flux which is linking with the coil at any time, then what is the EMF that is developed in the coil? So the EMF can be obtained from Faraday's laws as E equal minus d phi upon dt. Or you can say E is equals to minus d dt of, substituting the value of phi, it is equals to Li. Or this induced EMF can be written as minus, because L is a constant, I'll take it outside and I will differentiate only the current inside the coil. Inside. Okay, I'll name this as equation 1 and this as equation number 2. Okay, so from these two equations we will define about the definition of self-inductance. Alright, so in equation 1, if the current, let's say, is equals to 1 unit, or I can say 1 ampere. So if I is 1, then phi is equals to how much? Phi is equals to L. So this means that the self-inductance of a coil is numerically equals to the magnetic flux which is linking with the coil when the current of 1 ampere is passing through the coil. Alright, so that is one definition. And from equation 2, if I substitute this di upon dt, let's say is equals to, again, 1 unit. When I say 1 unit, it means 1 ampere, because above we have current, so current is ampere, and time it is second. Or we can see like 1 ampere per second like this. So if di by dt, what is this di by dt? Di by dt is the rate of change of electric current. So if the rate of change of electric current is equals to 1 ampere per second, then what happens to E? From equation 2, E is equals to just minus L times, how much is this? This is 1. So 1 times minus L will be minus L. Okay. And please remember here that this negative sign, it is actually in accordance with Lenz's law. So, right, you can also omit this negative sign, okay, because we are not concerned about the directions. Here we are just talking only about the magnitude. So then, this self-inductance, from here, it is numerically equals to the EMF induced in the coil when a current of, when the current is changing at the rate of 1 ampere per second. So this is the second definition of self-inductance. Alright. Now we will come to the SI unit of self-inductance. Okay, looking from this equation 1, we have L is equals to phi upon I. What is phi? Magnetic flux. And this magnetic flux is measured in Weber. What is I? Current. Current is ampere. So Weber per ampere is the SI unit of self-inductance. Or this is equivalent to Henry. Okay. So again, I hope you know this Henry. It is the name of the scientist which first discovered about the inductions of coil. So therefore, in order to remember his name, the SI unit of this self-induction is given in his name. Right. Okay. So again, right, from this equation 2, if you find out L is equals to E by di upon dt. So we know the SI unit of EMF is volt, and the SI unit of current is ampere, and this is second. So volt per ampere second. This is also the SI unit of self-inductance. Again, this should be equivalent to Henry. Okay, so please note down here, there are two SI units of, the derived SI unit of self-inductance. We have two. One is Weber ampere and the other is volt per ampere second. And both of these units, it is equivalent to Henry. Okay.